Tonight, we're going to explore something that sounds like science fiction, but is actually one of the most inevitable events in our cosmic future: the day the sun eats the Earth. You've probably heard about red giant stars before, massive, swollen suns that consume everything in their path. But here's what most people don't realize. Our sun, the same reliable star that has warmed Earth for 4.5 billion years, will one day become one of these cosmic destroyers. And when it does, it won't just threaten Earth. It will likely devour it completely. But the real mystery isn't whether this will happen, it's what comes before. Because long before our sun swells large enough to physically consume our planet, something far more subtle and terrifying will occur. Earth will become uninhabitable under a sky that looks perfectly normal. The same sun, just slightly brighter, will slowly boil away our oceans and strip our atmosphere into space. By the end of tonight, you're going to understand exactly how stellar evolution works, why this fate is sealed in the physics of stars themselves, and why Earth's story ends not with fire, but with a gentle, inexorable betrayal of light. Before we dive in, if you enjoy this kind of deep exploration, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. You wake up this morning the same way humans have awakened for thousands of generations. Light creeps across your bedroom wall, perhaps filtering through curtains or blinds, casting familiar patterns of brightness and shadow. Maybe you feel warmth through the window glass as you reach for your coffee, or notice how the angle of illumination has shifted slightly from where it was last month. These moments are so ordinary, so deeply woven into the rhythm of human experience, that we rarely pause to consider their source. The sun rises, light arrives, day begins. It is the most reliable appointment in your life, kept with such precision that you could set every clock on Earth by its timing. But what you are witnessing each morning is not the simple switching on of some cosmic light bulb. You are observing the surface effects of something far more complex and magnificent. That golden light touching your wall represents the end result of a process that began deep within the sun's core, where temperatures reach 15 million degrees and pressures crush matter into states that exist nowhere else in the solar system. Every photon that warms your skin this morning began its journey in that inferno, slowly working its way outward through dense layers of stellar material, taking tens of thousands of years to travel from the core to the surface, then racing across 93 million miles of empty space in just 8 minutes to reach your window. The sun you see is not a lamp that someone turned on 4.5 billion years ago and forgot about. It is not a constant, unchanging beacon burning with the same intensity it had when Earth was young. The sun is a living system, a self-regulating fusion furnace that has been evolving since the moment it first ignited. It has a biography, a life story written in the language of nuclear physics and stellar mechanics, and like every living thing, it has a timeline that includes birth, maturity, old age, and eventual death. Right now, as you read these words, the sun exists in what astronomers call its main sequence phase. This is stellar middle age, the longest and most stable period of a star's existence. For stars like ours, this phase can last roughly 10 billion years, and our sun has been in this comfortable middle period for approximately 4.5 billion years already. In human terms, if the sun's total main sequence lifetime were compressed into a single day, it would currently be late afternoon, perhaps around 4 or 5 o'clock. Not young, but far from elderly. Mature, stable, reliable. During this main sequence phase, the sun maintains what physicists call hydrostatic equilibrium. Deep in its core, the immense gravitational force of its own mass tries to crush the star inward, compressing matter toward the center with tremendous pressure. But nuclear fusion pushes back with equal force, generating energy and outward pressure that prevents gravitational collapse. These two fundamental forces, gravity and fusion pressure, exist in perfect balance, creating a stable system that can burn steadily for billions of years without significant change. Yet even this stability contains subtle variations. The sun you see today is not identical to the sun that shone on the first simple life forms in Earth's ancient oceans. It has been slowly, almost imperceptibly, growing brighter throughout its main sequence lifetime. This brightening happens so gradually that no human civilization could ever detect it directly. The increase amounts to roughly 1% brighter every 100 million years, or about 10% per billion years. These are changes measured against geological timescales, invisible to human perception, but profound in their cumulative effects. This gradual brightening occurs because of changes happening deep within the sun's core. As hydrogen fuses into helium over billions of years, the core's composition slowly shifts. Helium atoms are more massive than hydrogen atoms, so as helium accumulates in the center of the star, the core becomes denser. This increased density allows the fusion reactions to proceed more efficiently, generating slightly more energy and making the sun marginally brighter with each passing epoch. When you step outside on a clear morning and feel sunlight on your face, you are experiencing the end product of this ancient ongoing process. The warmth you feel represents nuclear energy that was generated in conditions more extreme than anything humans have ever created. Energy that has traveled an almost impossible distance to reach you, carrying with it the signature of stellar evolution that has been proceeding since before Earth had continents or oceans or life. The sun appears constant to us because human lifespans are vanishingly brief compared to stellar timescales. Your great-grandmother saw essentially the same sun you see today. Your great-grandchildren will see the same sun you see today. Even if human civilization persists for 10,000 years or 100,000 years, the sun will appear virtually unchanged to every generation. This apparent constancy is one of the deep illusions of human experience, created by the vast difference between the timescales of human life and the timescales of cosmic change. But constancy is not the same as permanence. The sun that illuminates your world today is a middle-aged star following a precisely predictable evolutionary path. Its nuclear fuel supply is finite. Its structure will change. Its brightness will increase. And eventually, billions of years from now, it will exhaust the hydrogen in its core and begin the transition into the final phases of stellar evolution. When that happens, the reliable, steady sun of human experience will transform into something entirely different, something that will remake the inner solar system and determine the ultimate fate of every world that orbits it, including Earth. When physicists use the word stable to describe our sun, they are employing a very specific definition that carries profound implications for understanding stellar behavior. In everyday language, stable might mean unchanging, constant, or predictable. But in the precise vocabulary of astrophysics, stellar stability refers to something more nuanced and ultimately more fascinating. It describes a dynamic equilibrium, a carefully balanced dance between competing forces that creates the illusion of constancy while allowing for slow, inexorable change. To understand what makes a star stable, you must first picture the sun as an enormous sphere of gas held together entirely by its own gravity. Every atom in the sun, from its outermost atmosphere down to its dense core, experiences the gravitational pull of every other atom. This creates an immense inward pressure, trying to compress the entire star down to the smallest possible volume. If gravity were the only force acting on the sun, it would collapse catastrophically in a matter of minutes, crusting down to a dense point and releasing tremendous energy in the process. But gravity does not act alone. Deep within the sun's core, where temperatures exceed 15 million degrees, and pressures reach more than 200 billion times the atmospheric pressure at Earth's surface, nuclear fusion creates an outward pressure that pushes back against gravitational collapse. Every second, roughly 600 million tons of hydrogen fuse into helium in the Sun's core, converting a tiny fraction of that mass directly into energy, according to Einstein's famous equation. This energy manifests as intense heat and radiation pressure that works its way outward through the Sun's interior, creating an expansive force that exactly balances the inward pull of gravity. This balance between gravitational compression and fusion pressure is what physicists call hydrostatic equilibrium. The Sun exists in a state where every layer, from the core to the surface, experiences forces that are perfectly matched. Gravity pulls inward with a specific strength at each depth, and the pressure gradient pushes outward with exactly the right intensity to prevent either collapse or expansion. This equilibrium is not static but rather dynamic, constantly maintained by the Sun's internal mechanisms, like a tightrope walker, making continuous tiny adjustments to maintain balance. What makes this balance so remarkable is its self-regulating nature. If the fusion reactions in the core were to suddenly increase in intensity, the additional energy and pressure would cause the core to expand slightly, which would lower its density and temperature, which would in turn reduce the fusion rate back to equilibrium. Conversely, if fusion were to slow down, the core would contract under gravity, raising its temperature and density until fusion increased again. The Sun essentially acts as its own thermostat, automatically adjusting its internal conditions to maintain stable energy production. This self-regulation is what allows main sequence stars like the Sun to burn steadily for billions of years without dramatic changes in their basic properties. The mass, radius, surface temperature, and luminosity of the Sun have remained within a relatively narrow range throughout the 4.5 billion years of Earth's existence. This stability provided the consistent energy input that allowed life to evolve and flourish on our planet, creating the predictable day-night cycles and seasonal patterns that have shaped the development of every ecosystem on Earth. But here is where the story takes its first subtle turn toward complexity. Even within this framework of stellar stability, the Sun is not truly constant. The hydrostatic equilibrium that maintains the Sun's overall structure cannot prevent slow changes in the star's internal composition, and these changes have consequences that accumulate over geological timescales. As hydrogen fuses into helium in the Sun's core, the fundamental character of that core slowly shifts. Helium nuclei are nearly 4 times more massive than hydrogen nuclei, so as fusion proceeds, the core becomes progressively denser. This increased density allows the existing fusion reactions to proceed more efficiently, extracting energy from hydrogen at a slightly higher rate. The result is a gradual increase in the Sun's energy output, a brightening so slow that it would be impossible to detect within human lifetimes, but profound when measured against the deep time of stellar evolution. Current models of stellar evolution suggest that this brightening proceeds at roughly 1% per 100 million years, or approximately 10% per billion years. These numbers might seem abstract, but they represent a fundamental transformation in the character of our star. The Sun that illuminated Earth's first bacterial mats 3.5 billion years ago was measurably dimmer than the Sun you see today. The Sun that will shine on Earth 1 billion years from now, assuming our planet still exists, will be noticeably brighter than the one that warms your face this morning. This gradual brightening represents the first crack in our intuitive understanding of solar constancy. When you imagine the Sun as a reliable, unchanging presence in the sky, you are thinking on human timescales where this evolutionary process is invisible. But when you expand your perspective to encompass the full lifetime of stars and planets, you begin to see that stability in astrophysics does not mean stillness. It means controlled change, predictable evolution, a slow transformation that operates according to physical laws but nevertheless leads toward a fundamentally different future. The implications of this realization extend far beyond academic stellar physics. If the sun's brightness has been slowly increasing throughout Earth's history, and if this increase will continue into the future, then the energy balance that has allowed liquid water to exist on our planet's surface for billions of years is not a permanent feature of the solar system. It is a temporary condition, a window of habitability that opened in Earth's past and will eventually close in Earth's future, not through any cosmic catastrophe or sudden change, but through the quiet, inexorable evolution of the star that gives us life. The destination of our story is written in the fundamental physics of stellar evolution, as inevitable as sunrise and as precisely calculable as the orbit of planets. Billions of years from now, when the hydrogen fuel in the sun's core finally becomes exhausted, our star will begin a dramatic transformation that will reshape the entire inner solar system. It will swell into a red giant, a luminous behemoth so enormous that its outer layers will extend far beyond the orbit of Mercury, possibly reaching Venus and quite likely engulfing Earth itself. This is the scenario that captures headlines and fires the imagination. The day the sun literally eats our planet, consuming it within its own expanded atmosphere like some cosmic act of cannibalism. The physics behind this transformation are well understood. When the hydrogen in the sun's core is finally depleted, the delicate balance between gravity and fusion pressure that has maintained our star's structure for 10 billion years will be disrupted. With no fusion reactions to generate outward pressure in the core, gravity will begin to win the ancient battle, compressing the helium-rich center to higher densities and temperatures. But this compression will have an unexpected consequence. The increased heat will ignite hydrogen fusion in a shell surrounding the inert core, and this shell burning will actually produce more energy than the sun generates today. This excess energy will cause the sun's outer layers to expand dramatically. The star's radius will grow by factors of hundreds, transforming our compact yellow sun into a bloated red-orange giant whose surface extends across millions of miles. Current models of stellar evolution suggest that at the peak of its red giant phase, the sun's photosphere may reach approximately 1.2 astronomical units from its center. Since Earth orbits at exactly 1 astronomical unit, this means the sun's visible surface could extend beyond our planet's current position, making physical engulfment not just possible, but likely. The fate of Mercury appears sealed beyond any reasonable doubt. The innermost planet orbits at just over 3/10 of an astronomical unit from the Sun, placing it well within even conservative estimates of the red giant's minimum size. Mercury will almost certainly be swallowed, its rocky surface vaporized, and its material incorporated into the Sun's outer atmosphere. Venus, orbiting at 7/10 of an astronomical unit, faces a similar destiny. The second planet may survive if the Sun's expansion falls on the smaller end of current projections, but most models place Venus within the red giant's envelope as well. Earth's situation is more complex and has been the subject of detailed computational studies. Several factors complicate the simple question of whether our planet will be physically consumed. As the Sun loses mass through stellar winds during its red giant phase, Earth's orbit will gradually expand outward, potentially carrying it beyond the reach of the swelling solar envelope. However, if Earth does survive the initial expansion and finds itself orbiting within the Sun's extended atmosphere, tidal interactions and atmospheric drag will cause our planet's orbit to decay rapidly, leading to engulfment within a relatively short time. The most sophisticated models suggest that Earth's survival depends on circumstances that are currently beyond our ability to predict with complete certainty. If our planet's orbit expands to approximately 1.15 astronomical units during the Sun's mass loss phase, it might escape physical destruction. But if the orbital expansion is less dramatic, or if the Sun's radius grows larger than current median projections, Earth will join Mercury and Venus as material incorporated into our dying star's atmosphere. But here is the crucial reframing that transforms this entire narrative. Whether or not Earth is physically consumed by the red giant sun is ultimately irrelevant to the question of our planet's habitability. The dramatic finale of engulfment, while scientifically fascinating and visually spectacular, is not the real ending of Earth's story as a living world. It is merely the final punctuation mark on a sentence that will have been completed billions of years earlier. Earth's habitability will end not with the violent drama of stellar consumption, but with the quiet, inexorable consequences of the gradually brightening sun we discussed in our previous exploration. Long before our star swells into a red giant, long before its surface reaches anywhere near Earth's orbit, the slow increase in solar luminosity will have already transformed our planet into a sterile, lifeless world stripped of its oceans and atmosphere. This represents one of the most profound inversions in our understanding of cosmic endings. Popular imagination focuses on the spectacular moment of physical destruction, the day when Earth's surface melts within the Sun's extended atmosphere. But the actual death of our world will occur in an environment that looks deceptively normal. The Sun will appear essentially unchanged to any observer who might witness Earth's final habitability crisis. It will be the same yellow star, burning in the same familiar patterns, following the same predictable, daily and seasonal cycles that have characterized human experience throughout history. Yet this apparently normal sun will deliver just enough additional energy to trigger cascading changes in Earth's climate system. The additional warmth will increase evaporation from the oceans, loading the atmosphere with water vapor. Since water vapor is itself a greenhouse gas, this will trap additional heat, accelerating the warming and creating a runaway feedback loop. Eventually, the upper atmosphere will become saturated with water vapor, allowing hydrogen to escape to space. Over geological time, Earth's oceans will literally evaporate away, molecule by molecule, leaving behind a desiccated world orbiting beneath a still familiar sky. This is the true ending of Earth's biological story, not fire and consumption, but slow suffocation under a brightening sun. Not the dramatic expansion of a dying star, but the quiet arithmetic of increasing luminosity. Not a cosmic catastrophe, but a gentle betrayal by the same reliable star that made life possible in the first place. The planet may survive to face the red giant phase billions of years later, but by then it will have been dead for eons. A lifeless rock whose fate becomes merely an academic question in stellar physics, rather than a meaningful chapter in the story of life in the universe. To understand how the sun sustains itself and why its future is so precisely predictable, you need to grasp one of the most elegant transactions in the universe: the conversion of matter into energy through nuclear fusion. This process operates like a cosmic banking system, where the sun pays its enormous energy bills by spending a currency more fundamental than anything humans have ever conceived. It trades mass itself, converting tiny amounts of matter into vast quantities of light and heat through mechanisms that transform the very identity of atomic nuclei. Deep within the sun's core, where temperatures reach 15 million degrees Celsius and pressures exceed 200 billion times Earth's atmospheric pressure, hydrogen nuclei overcome their natural electrical repulsion and fuse together to create helium. This might sound like a simple chemical reaction, but it represents something far more profound than any chemistry you learned in school. Nuclear fusion operates at the level of atomic nuclei themselves, rearranging the fundamental building blocks of matter according to the precise rules of nuclear physics. The process begins with the simplest element in the universe: hydrogen. Each hydrogen nucleus consists of a single proton, carrying a positive electrical charge that naturally repels other positively charged protons. Under normal circumstances, this electrical repulsion prevents hydrogen nuclei from coming close enough to interact. But in the extreme conditions of the Sun's core, thermal energy provides hydrogen nuclei with enough kinetic energy to overcome their mutual repulsion and approach each other closely enough for the strong nuclear force to take effect. When this happens, a complex sequence of nuclear reactions transforms 4 hydrogen nuclei into one helium nucleus. The helium nucleus contains 2 protons and 2 neutrons, giving it nearly 4 times the mass of a hydrogen nucleus. But here lies the crucial detail that powers every star in the universe. The helium nucleus produced by this fusion process has slightly less mass than the 4 hydrogen nuclei that created it. The difference amounts to approximately 0.7% of the original hydrogen mass, a seemingly tiny discrepancy that has enormous consequences. This missing mass does not simply disappear. According to Einstein's famous equation relating mass and energy, it transforms directly into energy with an efficiency that staggers the imagination. 0.7% of the Sun's hydrogen mass, when converted to energy, generates enough power to illuminate and warm the entire solar system for billions of years. Every second, the Sun converts approximately 4 million tons of matter into pure energy through this process. Yet this represents such a tiny fraction of the Sun's total mass that it can sustain this rate of conversion for roughly 10 billion years without exhausting its hydrogen fuel supply. The energy released by fusion manifests initially as high-energy gamma rays and neutrinos produced in the nuclear reactions themselves. The neutrinos escape from the Sun almost immediately, streaming through the solar material as if it were transparent and reaching Earth in just 8 minutes. But the gamma rays begin a much longer journey. They interact constantly with the dense material of the Sun's interior, being absorbed and re-emitted countless times as they work their way from the core toward the surface. This process can take tens of thousands of years, with each photon following a random walk through the Sun's layers, gradually losing energy and shifting toward longer wavelengths as it moves outward. But fusion produces more than just energy. It also creates a specific type of nuclear waste that accumulates in the Sun's core over cosmic timescales. The helium nuclei produced by hydrogen fusion are the ash of stellar burning, and unlike the ash from a wood fire, this stellar ash cannot be easily removed from the combustion zone. Helium nuclei are more massive than hydrogen nuclei, so they tend to settle toward the center of the Sun under the influence of gravity, gradually building up in the core region where fusion occurs most actively. This accumulation of helium ash has profound long-term consequences for the Sun's structure and behavior. As the core's helium content increases and its hydrogen content decreases, the fundamental properties of the core material begin to change. Helium nuclei require higher temperatures and pressures to undergo fusion reactions compared to hydrogen, so as helium accumulates, the conditions necessary to maintain energy production shift toward more extreme values. The Sun responds to this challenge by gradually contracting its core, raising the temperature and pressure until hydrogen fusion can continue at the rate necessary to balance the star's energy output. This core contraction explains why the Sun has been slowly brightening throughout its main sequence lifetime. As the core becomes denser and hotter to maintain fusion in an increasingly helium-rich environment, the efficiency of the fusion reactions increases, producing slightly more energy and making the Sun marginally brighter with each passing epoch. Currently, after 4.5 billion years of steady hydrogen burning, the Sun's core contains a substantial mixture of hydrogen and helium. Roughly 73% of the core's mass still consists of hydrogen available for fusion, while about 25% has been converted to helium ash. The remaining 2% consists of heavier elements that were present when the Sun first formed from the collapse of an interstellar gas cloud. This composition identifies our Sun as what astronomers call a population 1 star, a hydrogen-helium star with a small but significant complement of heavier elements produced by previous generations of stars. The Sun's nuclear identity card, written in the language of its elemental composition, tells the story not just of its own 4.5 billion year history of fusion, but also of the cosmic chemical evolution that preceded its formation. As this stellar evolution continues, the accumulation of helium ash will eventually reach a critical threshold. When the hydrogen in the core becomes sufficiently depleted and the helium content sufficiently enriched, the delicate balance that has maintained the Sun's stable main sequence burning for billions of years will finally be disrupted, setting in motion the sequence of structural changes that will transform our familiar yellow star into something entirely different. The story of solar brightening unfolds not as a dramatic crescendo, but as the slowest possible curve, a change so gradual that it challenges human comprehension of time itself. If you could somehow observe the Sun across its entire 10 billion year main sequence lifetime, you would witness an increase in brightness so subtle that detecting it would require the most sensitive instruments imaginable, measurements precise enough to distinguish between the energy output of consecutive geological epochs. Yet this barely perceptible drift in luminosity represents one of the most consequential processes occurring in our solar system, a gentle transformation that will ultimately determine the fate of every world orbiting our star. The physics driving this slow brightening lies in the fundamental chemistry of stellar evolution, specifically in how the accumulation of helium ash in the Sun's core gradually alters the conditions required to maintain fusion reactions. As we explored in our previous discussion, hydrogen fusion produces helium nuclei that are nearly 4 times more massive than the hydrogen nuclei they replace. Over millions of centuries, these heavier helium nuclei settle toward the center of the Sun's core under gravitational influence, creating a region that becomes progressively more helium-rich and hydrogen-poor as stellar evolution proceeds. This changing composition forces the Sun's core to work harder to maintain the same level of energy production. Helium nuclei fuse at much higher temperatures than hydrogen nuclei, so as the core's helium content increases, the existing hydrogen fusion reactions must occur in an environment that becomes gradually more compressed and heated. The Sun accomplishes this by slowly contracting its core, raising both temperature and pressure until the reduced hydrogen content can still generate enough energy to balance the star's gravitational compression. But this core contraction has an unexpected consequence. As the core becomes denser and hotter, the efficiency of hydrogen fusion actually increases. The higher temperatures and pressures allow the remaining hydrogen to burn more completely and at a slightly faster rate than before. This increased efficiency translates directly into higher energy production, making the Sun marginally brighter with each passing epoch of stellar evolution. The numbers that describe this process seem almost insignificantly small when expressed in human terms. Current models suggest the Sun brightens by approximately 1% every 100 million years, or roughly 10% per billion years. To put this in perspective, the difference between the Sun's brightness today and its brightness when dinosaurs first appeared on Earth 65 million years ago amounts to less than 1%. Even across the entire span of complex life on our planet, covering roughly 500 million years, the Sun has brightened by only about 5%. Yet when you expand this timeline to encompass the full geological history of Earth, the cumulative effect becomes profound. The Sun that illuminated our planet when the first bacterial mats began producing oxygen roughly 2.5 billion years ago was approximately 25% dimmer than the Sun you see today. The star that will shine on Earth 1 billion years from now, if our planet still retains its current orbit, will be roughly 10% brighter than the one that currently warms your face. This gradual brightening places Earth in an increasingly precarious position relative to the energy balance that has allowed liquid water to exist on our planet's surface throughout geological history. Earth's climate system has evolved within the context of a specific range of solar energy input, developing complex feedback mechanisms that have maintained relatively stable global temperatures despite dramatic changes in atmospheric composition, continental configuration, and biological activity over billions of years. But this remarkable climate stability depends fundamentally on Earth receiving an amount of solar energy that falls within certain bounds. Too little energy, and the planet would freeze into a permanent ice age, with oceans locked in solid form and life relegated to whatever minimal habitats might exist around geothermal vents. Too much energy, and the delicate balance that allows water to remain liquid at Earth's surface would be overwhelmed, leading to runaway greenhouse conditions that would eventually boil away the oceans entirely. Earth currently occupies what astronomers call the habitable zone around the Sun, the range of orbital distances where liquid water can theoretically exist on a planetary surface. But this zone is not fixed in space. As the Sun gradually brightens, the habitable zone slowly migrates outward, moving away from the Sun as increased stellar luminosity makes inner regions too hot to support liquid water. This migration occurs so slowly that it would be invisible to human observation across thousands of generations. Yet it represents a fundamental shift in the solar system's architecture, a quiet rearrangement of the conditions that determine where life can exist. Earth, locked in its current orbit by the gravitational dynamics of the solar system, cannot migrate outward along with the habitable zone. Instead, our planet will gradually find itself receiving more solar energy than its climate system can accommodate through natural regulatory mechanisms. The universe, it seems, rarely ends things with explosions or dramatic catastrophes. Instead, it tends to conclude chapters through increments, through the patient accumulation of small changes that eventually cross critical thresholds. The death of Earth's habitability will not announce itself with spectacular fireworks or sudden transformation. It will arrive through the arithmetic of gradually increasing luminosity, the quiet betrayal of a star that has nurtured life for billions of years, gradually becoming too generous with its energy. This represents one of the most poignant ironies in the story of planetary evolution. The same nuclear processes that have made Earth habitable throughout its history will eventually render it uninhabitable. The steady, reliable fusion reactions that have powered photosynthesis and driven weather patterns and maintained the water cycle will continue operating with perfect fidelity to the laws of physics, yet their gradual intensification will ultimately sterilize the very world they once sustained. The Sun will not turn hostile or malfunction or deviate from its prescribed evolutionary path. It will simply continue being exactly what it has always been, a main sequence star following the inexorable logic of stellar physics toward its predetermined future. The concept of a habitable zone around a star sounds almost poetic when first encountered, conjuring images of some cosmic sweet spot where conditions align perfectly for life. But strip away the appealing metaphor, and you discover something far more precise and ultimately more fascinating, a set of physical constraints that emerge from the fundamental properties of matter, energy, and planetary atmospheres. The habitable zone is not a destination that planets choose to occupy, but rather a consequence of how stellar radiation interacts with planetary surfaces and atmospheres according to the inexorable laws of thermodynamics and chemistry. To understand what makes a region of space habitable, you must first consider the specific requirements that liquid water imposes on any world where it might exist. Water remains liquid only within a relatively narrow temperature range under the pressure conditions that characterize most planetary surfaces. Too cold, and water freezes into ice, locking away the fluid medium that appears essential for the complex chemistry of life as we understand it. Too hot, and water vaporizes into steam, again eliminating the liquid phase that serves as both a chemical solvent and a medium for the molecular interactions that drive biological processes. But temperature alone does not determine habitability. The pressure at a planet's surface plays an equally crucial role in determining whether liquid water can exist. At very low pressures, water boils at temperatures far below what we consider normal, making it impossible for liquid water to remain stable even at moderate temperatures. At extremely high pressures, water can remain liquid at temperatures that would normally cause it to vaporize, but such conditions create other challenges for the chemistry of life. The habitable zone represents the range of distances from a star where a planet with an Earth-like atmosphere and surface pressure can maintain liquid water on its surface. This zone is determined primarily by the star's luminosity and the efficiency with which different atmospheric compositions can trap and redistribute the energy received from stellar radiation. For our Sun, the habitable zone extends roughly from 95 million miles to 170 million miles from the star's center, with Earth comfortably positioned at 93 million miles from the Sun. But this comfortable positioning masks a more complex reality. Earth's habitability depends not just on its distance from the Sun, but on a delicate interplay of atmospheric composition, greenhouse gas concentrations, ocean circulation patterns, cloud formation processes, and surface reflection properties that together regulate the planet's temperature. The greenhouse effect, often discussed in the context of climate change, actually represents the fundamental mechanism that makes Earth habitable. Without greenhouse gases like water vapor, carbon dioxide, and methane in our atmosphere, our planet would be approximately 60 degrees Fahrenheit colder than it actually is, cold enough to freeze most surface water despite our position within the Sun's habitable zone. This greenhouse regulation operates through a complex balance between incoming solar energy and outgoing thermal radiation. The Sun delivers energy to Earth primarily in the form of visible light, which passes relatively easily through our atmosphere and warms the planet's surface. The warmed surface then radiates energy back towards space in the form of infrared thermal radiation. Greenhouse gases in the atmosphere absorb some of this outgoing thermal radiation and re-emit it in all directions, effectively trapping energy within the Earth's climate system and raising the planet's average temperature above what it would be with no atmosphere at all. The precise balance of this greenhouse effect determines whether a planet within the habitable zone actually maintains habitable conditions. Too little greenhouse warming and surface water freezes despite adequate stellar energy input. Too much greenhouse warming and surface temperatures rise beyond the range where liquid water can exist, regardless of the planet's distance from its star. Venus provides a sobering example of how this balance can go catastrophically wrong. Our neighbouring planet orbits at 72% of Earth's distance from the Sun, placing it near the inner edge of the habitable zone where, in principle, liquid water should be able to exist. Venus receives roughly twice as much solar energy per unit area as Earth, but with an appropriate atmospheric composition, the planet could theoretically maintain moderate surface temperatures and potentially support liquid water. Instead, Venus has become a cautionary tale of runaway greenhouse warming. The planet's thick atmosphere consists of roughly 96% carbon dioxide, creating such an intense greenhouse effect that surface temperatures reach approximately 900 degrees Fahrenheit, hot, enough to melt lead and far beyond the temperature range where liquid water can exist under any pressure conditions. The atmospheric pressure at Venus's surface exceeds Earth's sea level pressure by a factor of 90, creating conditions so extreme that the few spacecraft that have successfully landed on the planet have survived only minutes before being destroyed by the hostile environment. Venus and Earth receive energy from the same sun, orbit within the same stellar system, and formed from similar materials in the same region of the early solar nebula. Yet these neighbouring worlds have evolved toward completely different climatic states, demonstrating how sensitive planetary habitability can be to atmospheric composition and greenhouse gas concentrations. The physics that govern both planets are identical, but the outcomes could not be more different. This comparison illuminates a crucial vulnerability in Earth's long-term habitability. As the sun gradually brightens over geological time, our planet will receive steadily increasing amounts of energy, potentially pushing Earth's climate system beyond the regulatory mechanisms that have maintained habitable conditions for billions of years. The same greenhouse effect that currently makes our world comfortable could become amplified by increasing solar input, potentially driving Earth toward Venus-like conditions despite our more favourable orbital distance. The habitable zone around the Sun is not a fixed region of space, but a slowly moving boundary that migrates outward as stellar luminosity increases. Earth, locked in its current orbit by gravitational dynamics, cannot follow this migration. Instead, our planet will gradually transition from a world comfortably within the habitable zone to one receiving energy levels that challenge the delicate balance between greenhouse warming and thermal regulation that has sustained liquid water on Earth's surface throughout the history of life. Water occupies a unique position in Earth's climate system, serving simultaneously as the planet's most important temperature regulator and its most dangerous potential destabilizer. This dual nature emerges from water's fundamental physical properties and its pervasive presence throughout Earth's atmosphere, oceans, and surface processes. Under current conditions, water acts like a planetary thermostat, absorbing excess heat through evaporation, transporting that energy through atmospheric circulation, and releasing it through precipitation and condensation in a continuous cycle that helps moderate global temperatures. Yet this same regulatory system contains within itself the seeds of its own destruction, a feedback mechanism that could ultimately transform Earth's benign climate into something far more hostile. The thermostat function of water operates through the planet's hydrological cycle, one of the most elegant regulatory systems in nature. When solar energy heats Earth's surface, it drives evaporation from oceans, lakes, rivers, and soil, converting liquid water into invisible water vapor that rises into the atmosphere. This evaporation process absorbs tremendous amounts of energy, approximately 540 calories per gram of water, effectively removing heat from the surface and transporting it upward into the atmosphere. The water vapor then travels through atmospheric circulation patterns, eventually condensing back into liquid droplets in clouds, releasing that stored energy as latent heat and precipitating back to the surface as rain or snow. This cycle serves as a massive heat engine that redistributes energy across the planet, moderating temperature extremes and preventing any single region from becoming too hot or too cold. Tropical regions, which receive intense solar heating, export excess energy through evaporation and atmospheric circulation to polar regions, which receive less direct solar input. The result is a global climate system that maintains relatively stable average temperatures despite enormous variations in energy input across different latitudes and seasons. But water vapor is not merely a passive participant in this regulatory system. It is also one of the most important greenhouse gases in Earth's atmosphere, capable of trapping outgoing thermal radiation and warming the planet's surface. This creates a fundamental feedback loop that operates at the heart of Earth's climate system. As temperatures rise, more water evaporates into the atmosphere, increasing the concentration of water vapor and enhancing the greenhouse effect, which causes additional warming, which drives more evaporation, which strengthens the greenhouse effect further. Under normal circumstances, this water vapor feedback is held in check by other regulatory mechanisms. Increased evaporation leads to more cloud formation, and clouds can either warm or cool the planet depending on their altitude, thickness, and composition. Low, thick clouds tend to reflect incoming solar radiation back to space, providing a cooling effect that can counteract greenhouse warming. High, thin clouds tend to trap outgoing thermal radiation while allowing most incoming solar energy to pass through, amplifying the warming effect. The balance between these competing influences helps determine whether the water vapor feedback leads to runaway warming or remains within manageable bounds. Current climate models suggest that as long as solar energy input remains within certain limits, Earth's water cycle can continue to function as a thermostat, absorbing and redistributing excess energy while maintaining conditions compatible with liquid water on the surface. But these same models reveal that the regulatory system has fundamental limits beyond which it cannot maintain stability. As solar energy input increases beyond critical thresholds, the water vapor feedback can overwhelm the cooling mechanisms that currently keep it in balance, transforming water from a thermostat into what climate scientists describe as a fuse. The transformation occurs through two distinct but related pathways that represent different doors leading to the same ultimate destination: the loss of Earth's oceans. The first pathway, known as the moist greenhouse scenario, begins when increased solar heating drives so much evaporation that water vapor penetrates high into the stratosphere, a region of the atmosphere that normally remains quite dry. Once water vapor reaches these high altitudes, ultraviolet radiation from the sun can break apart water molecules through a process called photodissociation, splitting them into hydrogen and oxygen atoms. Hydrogen, being the lightest element, can escape from Earth's gravity field once it reaches the upper atmosphere. Over geological timescales, this hydrogen escape represents a permanent loss of water from the planet's inventory. The oxygen left behind can combine with surface rocks through oxidation reactions, but the hydrogen is gone forever, carried away into interplanetary space by solar winds and thermal processes. The moist greenhouse scenario represents a slow leak of Earth's oceans into space, a gradual desiccation that could unfold over hundreds of millions of years. The second pathway, the runaway greenhouse scenario, represents a more dramatic escalation of the water vapor feedback. In this case, increasing solar energy drives evaporation at rates that overwhelm the atmosphere's ability to condense water back into precipitation. Surface temperatures rise high enough that the oceans begin to boil, loading the atmosphere with such enormous quantities of water vapor that the greenhouse effect becomes self-reinforcing beyond any possibility of regulation. Under runaway greenhouse conditions, surface temperatures can rise to several hundred degrees, hot enough to vaporize not just the oceans, but also any liquid water trapped in rocks, soil, or polar ice. The entire planet's water inventory becomes part of a thick, steamy atmosphere that traps heat so efficiently that surface conditions become incompatible with any form of life as we understand it. Both pathways represent different responses to the same underlying driver, the gradual increase in solar luminosity that will characterize the sun's continued evolution along the main sequence. They are like different doors opening onto the same hallway of increasing sunlight, each leading to the eventual elimination of liquid water from Earth's surface, but operating on different timescales and through different physical mechanisms. Whether Earth follows the slow path of hydrogen escape or the faster route of runaway greenhouse warming may depend on subtle details of atmospheric chemistry and climate sensitivity that remain at the cutting edge of current scientific understanding. The sequence of events that will eventually erase Earth's oceans from existence unfolds with the patient inevitability of physics itself, all Transformation so gradual that no human observer could witness its progression, yet so thorough that it will ultimately leave our planet as barren and dry as the surface of Mars. This process begins not with some dramatic climate catastrophe or sudden atmospheric collapse, but with the almost imperceptible intensification of familiar weather patterns that have characterized Earth's climate throughout human history. The same summer heat waves, the same humid afternoons, the same evaporation from lakes and rivers that you observe today will slowly intensify over geological timescales, driven by the gradual brightening of our sun as it continues its inexorable evolution along the main sequence. The initial stages of this transformation will manifest as a subtle shift in global climate patterns that might take millions of years to become clearly distinguishable from natural climate variability. Average global temperatures will rise by fractions of a degree per million years, a rate of change so slow that it would be undetectable within human lifespans but profound when accumulated across the deep time of planetary evolution. This warming will drive increased evaporation from Earth's surface waters, loading the atmosphere with higher concentrations of water vapor than have characterized our planet's climate system throughout the history of complex life. As water vapor concentrations increase, the greenhouse effect will intensify, trapping additional thermal radiation and accelerating the warming process through the feedback mechanisms we explored in our previous discussion. This enhanced greenhouse effect will drive even more evaporation, creating a self-reinforcing cycle that gradually pushes Earth's climate system away from the stable conditions that have maintained liquid water on the surface for billions of years. The cloud systems that currently help regulate Earth's temperature will begin to respond to these changing conditions in complex ways that remain at the frontier of climate science research. Higher atmospheric temperatures and increased humidity will alter cloud formation processes, potentially shifting the balance between high clouds that trap heat and low clouds that reflect sunlight back to space. Some models suggest that as the climate warms, cloud coverage patterns may change in ways that reduce the atmosphere's ability to reflect incoming solar radiation, further amplifying the warming trend. More critically, the increased water vapor will begin to penetrate higher into Earth's atmosphere than occurs under current conditions. The stratosphere, which today remains relatively dry, with water vapor concentrations of only a few parts per million, will gradually become more humid as intensified convection and altered atmospheric circulation patterns carry moisture to altitudes where it has rarely existed throughout Earth's climate history. This stratospheric moistening represents a crucial threshold in the planet's transition towards uninhabitability. In the stratosphere, water molecules encounter the full intensity of the sun's ultraviolet radiation, which carries enough energy to break apart water molecules through photodissociation. This process splits water into its component atoms, hydrogen and oxygen. The oxygen atoms can combine with other atmospheric constituents or react with surface materials, but the hydrogen atoms, being the lightest element in the periodic table, possess enough thermal energy to escape from Earth's gravitational field entirely. The hydrogen escape process operates like a slow leak in Earth's water inventory, removing water molecules permanently from the planet's hydrological system. Unlike other climate processes that redistribute water between oceans, atmosphere, ice, and groundwater, hydrogen escape represents a net loss of water from the Earth system, with the escaped hydrogen carried away into interplanetary space by solar winds and thermal motion. Initially, this hydrogen escape will occur at rates too small to significantly affect Earth's total water inventory. The planet's oceans contain approximately 1.4 billion cubic kilometers of water, an enormous reservoir that could sustain modest rates of hydrogen loss for hundreds of millions of years without dramatic changes in sea level or surface water availability. But as solar luminosity continues to increase, driving higher rates of evaporation and stratospheric humidity, the rate of hydrogen escape will accelerate accordingly. Current models of this process, while still subject to significant uncertainties, suggest several possible timelines for the eventual loss of Earth's surface water. Some calculations indicate that the transition to a moist greenhouse state, where significant hydrogen escape begins, could occur within approximately 1 billion years under the influence of natural solar brightening alone. Other models, incorporating different assumptions about cloud feedback processes and atmospheric chemistry, suggest timelines that could be several 100 million years longer or shorter. The uncertainty between these models reflects the enormous complexity of predicting how Earth's climate system will respond to conditions that have never existed in our planet's observable history. The interactions between atmospheric chemistry, cloud formation, ocean circulation, and biogeochemical cycles under extremely high temperature and humidity conditions involve processes that push current climate models to their limits and beyond. What remains consistent across different modelling approaches is the ultimate outcome, the gradual disappearance of liquid water from Earth's surface as the planet's water inventory slowly leaks into space. The coastlines that have defined human geography throughout history will retreat as ocean levels drop. Inland seas and freshwater lakes will shrink and eventually disappear as evaporation rates exceed precipitation in an increasingly hot and humid atmosphere. This transformation will proceed with eerie quietness, unmarked by the dramatic storms or atmospheric disturbances that characterize rapid climate changes. The sun will continue to rise and set with the same reliable rhythm that has characterized human experience throughout history. Seasons will continue to cycle according to Earth's orbital mechanics and axial tilt. Yet beneath this facade of normalcy, the planet will be slowly dying, losing the essential ingredient that made life possible in the first place. The final stages of this process will leave Earth as a desiccated world, its surface scarred by empty ocean basins and dry riverbeds, its atmosphere stripped of the water vapor that once moderated its climate, orbiting a sun that appears virtually identical to the star that once nurtured a blue and living world. Picture Earth in this distant future, perhaps 800 million years from now, when the sun has brightened by approximately 8% from its current luminosity. To an observer arriving from interstellar space, the sun would appear virtually identical to the familiar yellow star of today. Its surface temperature, its spectrum of emitted light, its rotation period, and its overall appearance would fall well within the normal range of variation that characterizes any star across shorter timescales. Yet this apparently unchanged sun now illuminates a world that has become utterly alien, transformed not through cosmic catastrophe or sudden upheaval, but through the patient arithmetic of increasing energy input accumulating across geological time. The transformation begins with the most fundamental change in Earth's geography, the steady retreat of coastlines as ocean levels drop year by year, century by century, millennium by millennium. The beaches where waves once broke now lie hundreds of miles inland from new shorelines. Ancient port cities that once bustled with maritime commerce sit stranded on dry land, their harbours filled with sediment and their docks extending towards seas that no longer exist. The continental shelves, once submerged beneath shallow seas that teemed with marine life, now stretch as vast coastal plains dotted with the fossilized remains of coral reefs and shellfish beds. The Pacific Ocean, once the largest feature on Earth's surface, has contracted into disconnected seas, separated by exposed seafloor ridges and volcanic chains that previously lay hidden beneath miles of water. The Mid-Atlantic Ridge, that great underwater mountain chain where new oceanic crust was born for hundreds of millions of years, now stands exposed as a terrestrial mountain range stretching from the Arctic to the Antarctic, its volcanic peaks no longer quenched by seawater, but cooling in the increasingly thin and humid atmosphere. As the oceans shrink, the remaining bodies of water become progressively more concentrated, with dissolved salts and minerals that were once distributed throughout much larger volumes. These remnant seas take on the character of vast salt lakes, their waters so saline that few forms of life can tolerate their chemistry. The biological productivity that once characterized Earth's marine ecosystems collapses as the fundamental basis of oceanic food chains disappears along with the water that sustained them. The atmosphere during this phase becomes almost unbearably humid by the standards of any climate that has existed in Earth's observed history. Relative humidity levels approach 100% across most of the planet's surface, creating conditions where human beings, had they somehow survived to witness this transformation, would find breathing difficult and temperature regulation impossible. The air itself becomes a thick, steamy medium that carries unprecedented amounts of water vapor, yet paradoxically signals the beginning of the end for liquid water on Earth's surface. Weather systems during this period exhibit characteristics that stretch the very definition of familiar meteorological phenomena. The enormous quantities of water vapor in the atmosphere provide the energy potential for storms of extraordinary intensity, hurricanes and typhoons, with wind speeds and precipitation rates that dwarf anything recorded in human history. Yet these extreme weather events become increasingly rare and eventually disappear entirely as the source of their energy, the evaporation of surface water, gradually diminishes with the shrinking oceans. The final major storms of Earth's meteorological history occur as isolated, almost surreal events in a world where most weather patterns have already begun to fade. These storms draw their energy from the last substantial bodies of liquid water, creating towering thunderheads that reach unprecedented heights in the increasingly humid atmosphere, generating lightning displays and precipitation events of biblical proportions before dissipating into the steamy air, never to be replaced by similar phenomena. As surface water continues to disappear, these dramatic weather systems give way to an eerie atmospheric stillness that characterizes the planet's transition from a dynamic, water-rich world to a static, desiccated one. The jet streams that once drove global weather patterns weaken and eventually disappear as the temperature gradients that powered them diminish. The monsoons that brought seasonal rains to vast continental regions fade as the oceanic heat sources that generated them shrink and vanish. The biological collapse that accompanies this transformation occurs with the same quiet inevitability that characterizes the physical changes in Earth's surface and atmosphere. Ecosystems that evolved over hundreds of millions of years to depend on specific temperature ranges, humidity levels, and precipitation patterns find themselves unable to adapt to the rapidly changing conditions. Forests that once covered entire continents wither and die, not from fire or disease, but from the simple inability of their root systems to extract enough water from increasingly dry soils. The great grasslands that sustained vast herds of mammals disappear as the grasses themselves cannot survive the combination of extreme heat and diminishing precipitation. Marine ecosystems collapse as their oceanic habitats literally evaporate away. Even the most resilient forms of life, the bacteria and archaea that have survived every previous mass extinction in Earth's history, find themselves challenged by conditions that exceed the physiological limits of any known living organism. Yet throughout this biological catastrophe, the sun continues to shine with the same steady reliability that has characterized its behavior throughout human history. Dawn breaks each day at the predicted time. Seasons cycle according to Earth's orbital mechanics. Solar eclipses occur precisely when astronomical calculations predict them. The star that once made Earth a garden continues to fulfill its role as a perfectly normal, middle-aged, main-sequence star, following the evolutionary pathway prescribed by stellar physics, with no deviation from the natural course of stellar development. This represents perhaps the most unsettling aspect of Earth's future transformation. The complete disconnection between the apparent normalcy of the solar system's primary energy source and the catastrophic changes occurring on the planet that depends on that energy. The sun betrays no sign of malfunction or abnormality. It simply continues being exactly what it has always been, while the cumulative effects of its gradual brightening render Earth progressively more alien with each passing epoch, transforming a living world into a sterile monument to the inexorable mathematics of stellar evolution. As Earth's surface water disappears through the slow leak of hydrogen escape, the planet's atmosphere begins to undergo a fundamental transformation that extends far beyond the simple loss of water vapor. The same physical processes that drive water molecules apart in the upper atmosphere also affect other atmospheric constituents, initiating a cascade of chemical and physical changes that will eventually strip away much of the protective, gaseous envelope that has shielded Earth's surface throughout the history of life. This atmospheric erosion occurs through multiple mechanisms operating simultaneously, each contributing to the gradual thinning of the air until what remains bears little resemblance to the atmosphere that once sustained a living world. Thermal escape represents the most straightforward of these atmospheric loss processes, operating according to the basic principles of kinetic theory and gravitational physics. In any gas, individual molecules move with a range of velocities determined by temperature, with some molecules moving much faster than the average while others move more slowly. At the very top of Earth's atmosphere, where the gravitational field is weakest and molecular collisions are rare, the fastest moving molecules can achieve velocities that exceed the planet's escape velocity, allowing them to break free from Earth's gravitational influence and drift away into interplanetary space. Under current conditions, thermal escape affects primarily the lightest atmospheric constituents, particularly hydrogen and helium atoms that reach the exosphere with sufficient kinetic energy to overcome Earth's gravity. Heavier molecules like nitrogen, oxygen, and carbon dioxide typically lack the thermal energy needed to escape, even at the elevated temperatures that characterize the upper atmosphere. But as the sun continues to brighten and Earth's surface temperatures rise, the enhanced heating of the upper atmosphere will increase the thermal energy of all atmospheric constituents, eventually allowing progressively heavier molecules to achieve escape velocities. The process accelerates through what atmospheric scientists call hydrodynamic escape, which occurs when atmospheric heating becomes so intense that the upper atmosphere begins to expand dramatically, reducing the effective gravitational binding energy that holds atmospheric gases to the planet. Under these conditions, atmospheric constituents that would normally be retained by Earth's gravity can be dragged away by the escaping flow of lighter elements, similar to how debris can be carried away by a rapidly flowing river, even if the debris itself would normally sink in still water. Non-thermal escape processes add additional complexity to the atmospheric loss equation, operating through mechanisms that do not depend directly on temperature, but rather on the electromagnetic environment surrounding Earth. Solar radiation, particularly in the ultraviolet portion of the spectrum, carries enough energy to ionize atmospheric molecules, stripping away electrons and creating charged particles that respond to magnetic and electric fields in ways that neutral molecules do not. These ionized atmospheric constituents can be accelerated to high velocities through interactions with the solar wind, the stream of charged particles that flows continuously outward from the sun. The solar wind carries its own magnetic field, which can interact with Earth's magnetic field and with ionized atmospheric particles in complex ways that sometimes result in atmospheric material being stripped away from the planet, despite having insufficient thermal energy to escape through purely thermal processes. The brightening sun intensifies all of these escape mechanisms simultaneously. Higher solar luminosity means more intense ultraviolet radiation reaching Earth's upper atmosphere, driving increased rates of photodissociation and ionization. The enhanced solar heating expands the upper atmosphere, reducing the gravitational binding energy that retains atmospheric gases. The stronger solar wind associated with a more luminous star creates more effective conditions for non-thermal atmospheric stripping. As these processes continue over hundreds of millions of years, Earth's atmospheric composition begins to shift in fundamental ways. Water vapor, already depleted through hydrogen escape, becomes an increasingly minor component of the atmosphere. Oxygen levels drop as oxygen atoms produced by photodissociation combine with surface rocks through oxidation reactions or escape to space along with hydrogen in the form of hydroxyl radicals. Carbon dioxide concentrations may initially increase as the oceans release dissolved gas, but eventually this too begins to escape or react with surface materials as atmospheric pressure drops below the levels where carbon dioxide can remain stable in gaseous form. The most dramatic change occurs in atmospheric pressure itself, which drops steadily as the total mass of atmospheric gases decreases through escape processes. Earth's current sea level atmospheric pressure of approximately 14.7 pounds per square inch represents the weight of the entire atmosphere pressing down on the surface. As atmospheric mass decreases through escape, this pressure drops correspondingly, eventually reaching levels where liquid water cannot exist at any temperature commonly found on planetary surfaces. At very low atmospheric pressures, water boils at temperatures far below its normal boiling point, making it impossible for any remaining surface water to persist in liquid form regardless of temperature conditions. This creates a feedback effect where the loss of atmospheric pressure accelerates the evaporation of any remaining surface water, which in turn accelerates atmospheric loss through the hydrogen escape processes we have already discussed. The end result of these interconnected processes is an Earth whose atmosphere bears no resemblance to the thick protective envelope that once sustained a biosphere. What remains may consist primarily of heavier gases like carbon dioxide and nitrogen that are more resistant to escape processes, but at pressures so low that they provide no meaningful protection against solar radiation and no capacity to support liquid water or the complex chemistry required for life. This transformed atmosphere hangs around a planet whose surface has been sterilized not through fire or impact or sudden catastrophe, but through the patient removal of the basic ingredients that made life possible. The rocks remain, scarred by ancient riverbeds and empty ocean basins. The continental masses persist, bearing the geological record of billions of years of biological activity now ended forever. But the air itself, that invisible medium that once carried the sounds of living creatures and the scents of flowering plants, has become a thin whisper of gas hovering above a world that remembers life only in stone. In the aftermath of Earth's atmospheric thinning and oceanic evaporation, when the great hydrological cycles that have shaped our planet's surface for billions of years finally cease their eternal circulation, the Earth enters a phase of existence unlike anything in its previous geological history. This is not death in any biological sense, for the planet itself remains structurally intact, its mass unchanged, its orbit stable, its rotation continuing with the same mechanical precision that has characterized its motion since the solar system's formation. Yet something profound has ended, something so fundamental to Earth's character that the planet becomes a fundamentally different kind of world, transformed from a dynamic, ever-changing sphere of rock, water, and air into something more static, more permanent, and ultimately more alien. The geological processes that have continuously reshaped Earth's surface throughout its 4.5 billion year history depend critically on the presence of liquid water as both a chemical agent and a physical medium for erosion, transport, and deposition. Without oceans to drive weather systems, without rivers to carry sediments from highlands to lowlands, without groundwater to facilitate chemical weathering of rocks, The dynamic equilibrium that has maintained Earth's geological activity begins to slow and eventually approaches a kind of suspended animation that could persist for billions of years. Erosion, that patient sculptor of landscapes that has carved the Grand Canyon, worn down entire mountain ranges, and redistributed the products of volcanic activity across continents, slows to rates that become negligible when measured against human timescales. The wind erosion that continues in the thin atmosphere can move only the finest particles, and with no hydrological cycle to replenish atmospheric moisture, dust storms become less frequent and less effective at reshaping surface features. The chemical weathering processes that gradually break down rock minerals in the presence of water and atmospheric gases slow dramatically as both water and many atmospheric constituents disappear from the surface environment. The sedimentary processes that have created layered rock formations throughout Earth's geological history essentially cease operation. Without rivers to transport eroded material from mountains to sea level, without ocean currents to distribute sediments across continental shelves, without seasonal cycles of freezing and thawing to fragment rock formations, the constant redistribution of surface materials that has characterized terrestrial geology throughout the planet's history comes to an end. The sediments that exist at the moment when Earth's hydrological systems fail become frozen in place, preserved for geological timescales as testimony to climatic conditions that no longer exist. This cessation of sedimentary activity means that the geological record of Earth's final phase as a living world becomes permanently fixed in rock formations that will persist essentially unchanged for hundreds of millions or even billions of years. Future geological investigators, whether terrestrial or extraterrestrial, could potentially read this record like the final chapter of a book, examining the last layers of sedimentary rock to understand the conditions that existed when Earth's biosphere collapsed and its surface water disappeared. The tectonic processes that have driven continental drift, volcanic activity, and mountain building throughout Earth's history face a more complex transformation in this waterless future. Plate tectonics depends not only on the heat engine of Earth's interior, but also on the lubrication provided by water in subduction zones, where oceanic plates dive beneath continental plates and descend into the mantle. Water facilitates the melting processes that generate magma and drive volcanic activity, and it affects the mechanical properties of rock at the high pressures and temperatures that characterize active plate boundaries. Without surface water to infiltrate into rock formations and eventually reach subduction zones, the character of plate tectonics may shift toward a different regime, perhaps more similar to the geological processes that operate on Venus, where extreme surface temperatures have eliminated liquid water and created a different style of crustal recycling. Volcanic activity may continue, but with different chemical compositions and eruption styles, as magmas generated, in the absence of water-rich conditions, exhibit different flow properties and gas contents than the volcanic rocks that have characterized Earth's geological history. The mountain ranges that currently mark the boundaries between tectonic plates will persist as monuments to Earth's former geological activity, but their continued growth and modification will slow dramatically. Without erosion to remove material from their peaks and slopes, mountains may actually grow taller over time as tectonic forces continue to operate without the counterbalancing effects of weathering and erosion that currently limit mountain heights on Earth. Ocean basins, those vast depressions that once held the waters that gave Earth its blue appearance from space, become permanent features of the planet's topography, preserved as empty basins that record the former extent of seas that no longer exist. These basins, lined with sediments that accumulated over hundreds of millions of years, become geological museums containing the fossilized remains of entire ecosystems that flourished when Earth was a living world. Salt deposits, formed through the evaporation of the last remnant seas, create vast crystalline plains that stretch across former seafloors like mineral snowfields. These salt formations, some potentially reaching thicknesses of hundreds or even thousands of feet, represent the concentrated chemical legacy of all the dissolved minerals that once cycled through Earth's hydrological systems. The salt deposits become among the most visible features of the transformed landscape, creating a geological signature that could be detected by future observers as evidence of the planet's former oceanic heritage. This long twilight phase of Earth's existence could persist for billions of years, maintained by the continued operation of the Sun as a main sequence star providing steady energy input to a world that can no longer make productive use of that energy. The planet continues to exist, continues to orbit, continues to receive sunlight and radiate heat back to space according to the fundamental laws of thermodynamics. Yet in every way that once mattered for the definition of Earth as a living world, the story has already ended, leaving behind only a sphere of stone and salt, orbiting a star that remembers nothing of the life it once sustained. While Earth undergoes its slow transformation from a living world to a sterile sphere of rock and salt, the Sun itself approaches a milestone that has been written into its stellar DNA since the moment nuclear fusion first ignited in its core 4.5 billion years ago. This transition represents not a malfunction or deviation from normal stellar behavior, but rather the natural progression of stellar evolution, as inevitable and predictable as the orbital mechanics that govern planetary motion. The Sun's middle age, that long period of stable hydrogen burning that has characterized its existence throughout Earth's history, gradually approaches its end through the same internal processes that have sustained it for billions of years. The approaching crisis begins with a simple accounting problem in the Sun's core. For 4.5 billion years, hydrogen nuclei in the central region of the Sun have been steadily fusing into helium nuclei, converting approximately 600 million tons of matter into energy every second through the nuclear processes we explored earlier in our journey. This fusion occurs most efficiently in the very center of the core, where temperatures and pressures reach their highest values, and where the density of hydrogen nuclei provides the most favorable conditions for nuclear reactions. But this preferential burning of hydrogen in the core's center creates a gradual depletion zone where the fuel that has powered the Sun throughout its main sequence lifetime becomes increasingly scarce. As hydrogen is consumed and converted to helium ash, the central region of the core slowly transforms from a hydrogen-rich environment optimized for fusion into a helium-rich environment where fusion becomes progressively more difficult to sustain. Helium nuclei require much higher temperatures and pressures to undergo fusion reactions compared to hydrogen nuclei. The process of helium fusion, which involves combining 3 helium nuclei to create carbon, demands core temperatures of approximately 100 million degrees, roughly 6 times hotter than the 15 million degree temperature required for hydrogen fusion. The current Sun simply does not possess the internal conditions necessary to burn helium, so as hydrogen becomes depleted in the core, the helium ash accumulates as inert material that contributes to the core's mass and gravitational influence, but produces no energy to support the Sun's luminosity. The Sun's response to this developing energy crisis follows the fundamental principles of stellar structure that have governed its behavior throughout its main sequence lifetime. As fusion reactions slow in the hydrogen-depleted center of the core, the energy production rate begins to drop below the level required to maintain the outward pressure that balances the Sun's gravitational self-attraction. With insufficient thermal pressure to resist gravitational compression, the core begins to contract under its own weight. This core contraction triggers a sequence of changes that initially seems to solve the energy problem, but ultimately leads the Sun inexorably toward the red giant transformation. As the core shrinks, gravitational compression raises both its temperature and density, creating more favorable conditions for hydrogen fusion in a shell surrounding the helium-rich center. This shell burning occurs in hydrogen-rich material just outside the inert helium core, where the increased temperature and pressure resulting from core contraction can sustain fusion reactions at rates that actually exceed the energy production of the current sun. The hydrogen-burning shell represents a fundamentally different mode of stellar energy production compared to the centralized core fusion that has characterized the sun throughout its main sequence phase. Shell burning tends to be less stable than core burning, prone to variations in energy output that translate into structural instabilities throughout the star. More importantly, shell burning typically produces more energy than core burning under similar conditions, providing the sun with energy sources that exceed its current luminosity and setting in motion changes that will transform the star's overall structure. The excess energy produced by efficient shell burning cannot be easily accommodated within the sun's current structural framework. The star's outer layers, which have been in hydrostatic equilibrium with the energy output of core hydrogen burning for billions of years, suddenly face energy inputs that exceed their capacity for thermal regulation. The additional energy drives expansion of the sun's envelope, causing the outer layers to swell as they attempt to radiate away the excess heat produced by shell burning. This expansion of the sun's outer layers marks the beginning of the red giant transformation, though the process unfolds over millions of years rather than occurring as a sudden transition. The expanding envelope causes the sun's surface to cool and redden as the same total luminosity spreads over a much larger surface area. The star grows in size while its surface temperature drops, transforming from the compact hot yellow star of the main sequence into the large, cool reddish star that defines the red giant phase. From the perspective of stellar evolution, this transition represents the sun's natural response to the changing fuel supply in its core. The same nuclear processes that have sustained stable energy production for 10 billion years eventually exhaust the hydrogen in the central burning region, forcing the star to find alternative sources of nuclear fuel. Shell burning provides that alternative, but at the cost of structural stability that will ultimately lead to more dramatic changes in the sun's size, luminosity, and effect on the surrounding solar system. This represents stellar middle age giving way to stellar old age, a transformation driven by the fundamental physics of nuclear burning and gravitational equilibrium. The sun does not choose this evolutionary pathway. It follows the trajectory prescribed by its mass, composition, and the laws of physics that govern stellar structure. The red giant phase represents not a deviation from normal stellar behavior, but the next chapter in a story that was written in nuclear physics billions of years ago, when the sun first began converting hydrogen into helium in its core and started the slow countdown toward this inevitable structural transformation. The transformation of our sun from a compact yellow main sequence star into a swollen red giant unfolds through a mechanism so elegant in its physics and so inexorable in its progression that it represents one of the most thoroughly understood processes in stellar evolution. This expansion occurs not through some external force acting upon the sun, but through the star's own internal response to changing conditions in its core, a response that follows the fundamental laws of stellar structure with mathematical precision. Understanding this process requires following the flow of energy from the sun's center outward through layers of stellar material, tracing how changes in the nuclear furnace deep within the star eventually manifest as dramatic alterations in the sun's size, surface temperature, and appearance. The driving force behind red giant expansion lies in the character of shell burning, the nuclear fusion process that replaces core hydrogen burning as the sun's primary energy source. Unlike the centralized fusion reactions that have occurred in the sun's core throughout its main sequence lifetime, shell burning takes place in a thin spherical region surrounding the inert helium core, where hydrogen-rich material encounters the elevated temperatures and pressures created by the contracting core's gravitational compression. This hydrogen-burning shell operates under more extreme conditions than the core fusion that preceded it. The shell experiences higher temperatures, greater pressures, and steeper temperature gradients than existed in the original core burning region. These intensive conditions make shell burning remarkably efficient at extracting energy from the available hydrogen, fuel, allowing fusion reactions to proceed at rates that significantly exceed the energy production levels that characterize the Sun during its main sequence phase. The enhanced efficiency of shell burning creates an energy surplus that the Sun's existing structure cannot easily accommodate. Throughout its 4.5 billion year main sequence lifetime, the Sun's outer layers have existed in hydrostatic equilibrium with a specific level of energy output from the core. Every layer of stellar material, from the core boundary to the visible surface, has adjusted its density, temperature, and pressure to balance the inward pull of gravity against the outward pressure created by the flow of energy from nuclear fusion. When shell burning begins producing more energy than core burning ever generated, this delicate equilibrium becomes disrupted throughout the star's interior. The excess energy flowing outward from the shell encounters stellar layers that were structured to handle lower energy fluxes, creating conditions where thermal pressure exceeds the gravitational compression that holds those layers in their current configuration. The Sun's response to this energy imbalance follows the path of least resistance according to stellar physics. The outer layers begin to expand. This expansion occurs gradually over millions of years as stellar material adjusts to the new energy regime, but the cumulative effect transforms the Sun's structure in dramatic ways. Layers of stellar material that currently exist at specific distances from the Sun's center slowly migrate outward, swelling the star's overall volume while decreasing the density of its outer regions. As the Sun's outer envelope expands, a fascinating consequence emerges from the relationship between surface area, luminosity, and temperature. The total energy output of the shell-burning Sun actually increases compared to its main sequence luminosity, as the more efficient fusion processes generate more power than the original core burning. However, this increased luminosity must radiate away from a surface that has expanded to cover a much larger area than the current Sun's photosphere. The physics of thermal radiation dictates that when the same amount of energy, or even somewhat more energy, must radiate from a larger surface area, the temperature of that surface must decrease to maintain the energy balance. This creates the characteristic appearance of red giant stars. They are more luminous than main sequence stars of similar mass, yet their surfaces are cooler and therefore appear reddish rather than yellow or white. The Sun's surface temperature during its red giant phase may drop from its current 5,800 degrees Kelvin to approximately 3,000 degrees Kelvin, cool enough to shift the peak of its thermal radiation from the yellow-green portion of the spectrum toward the red and infrared regions. Yet despite this surface cooling, the total energy output of the red giant Sun will exceed its current luminosity by factors of hundreds or even thousands, as the much larger surface area more than compensates for the decreased surface temperature. This combination of increased luminosity and expanded size creates conditions in the inner solar system that bear no resemblance to the stable energy environment that has characterized the Sun's main sequence phase. The same nuclear processes that currently provide Earth with the precise amount of energy needed to maintain liquid water and support life will generate energy outputs sufficient to vaporize rocky material at Earth's current orbital distance. The expanded Sun will also present a dramatically different appearance from any world that might survive in the outer solar system. Instead of the familiar point source of light that has defined solar illumination throughout human history, the red giant Sun will appear as a vast orange disk that subtends a significant fraction of the sky. From Earth's current orbital distance, If the planet somehow survived the initial expansion, the Sun's surface would appear hundreds of times larger in angular size than the full Moon, creating illumination conditions unlike anything that has existed in the solar system since its formation. The transformation occurs through the same fundamental processes that have governed the Sun's behavior for billions of years. No external intervention drives this change. No deviation from normal stellar physics causes the expansion. The red giant phase represents the natural continuation of stellar evolution, the inevitable result of nuclear fuel depletion in the core and the star's structural response to changing energy production mechanisms. This represents perhaps the most profound aspect of the red giant transformation. The sun that once warmed gardens and sustained life becomes a star that remakes the architecture of the entire inner solar system, not through malice or malfunction, but through the quiet, inexorable operation of the same physical laws that made life possible in the first place. The question of how large the sun will become during its red giant phase is not merely academic curiosity, but rather a matter of precise calculation that determines the fate of every world in the inner solar system. Stellar evolution models, refined through decades of research and validated against observations of red giant stars throughout the galaxy, provide remarkably specific predictions about the Sun's future dimensions. These models represent some of the most reliable forecasts in all of astronomy, grounded in well-understood physics and supported by extensive observational data from stars at various stages of evolution. When astronomers speak of the Sun's maximum size during its red giant phase, they typically reference the moment when the star reaches what is called the tip of the red giant branch, the point of maximum expansion, before helium fusion ignites in the core and causes the star to contract, somewhat. At this crucial moment in solar evolution, detailed computer models predict that the Sun's radius will extend to approximately 1.2 astronomical units from its center, a dimension that transforms our familiar star from a compact object barely larger than some planets into a cosmic giant whose surface reaches well beyond the orbit of Venus. To grasp the true scale of this transformation, you must first understand what an astronomical unit represents in physical terms. The astronomical unit, abbreviated as AU, is defined as the average distance between Earth and the Sun, approximately 93 million miles or 150 million kilometers. This distance serves as astronomy's most fundamental ruler for measuring the architecture of our solar system, the cosmic yardstick against which all other solar system dimensions are measured. When you step outside on a clear morning and look up at the Sun, you are seeing a star whose light has travelled exactly 1 astronomical unit to reach your eyes. The warmth you feel on your face has crossed this same distance, carrying energy that began its journey in the Sun's core tens of thousands of years ago and completed its voyage through the 93 million miles of interplanetary space in just 8 minutes and 20 seconds. This distance, so vast that light itself requires more than 8 minutes to traverse it, represents the baseline measurement for understanding the scale of the red giant transformation. A sun with a radius of 1.2 astronomical units would extend its visible surface to a distance 20% greater than Earth's current orbital distance from the center of the solar system. To visualize this scale, imagine Earth's entire orbit around the Sun compressed down to a circle that fits within the red giant's photosphere, with room to spare. The distance that currently separates our planet from our star, that fundamental gap across which solar energy travels to power life on Earth, becomes merely the radius of the transformed Sun's outer atmosphere. This expansion represents an increase in the Sun's radius by a factor of more than 200 compared to its current dimensions. The Sun's present radius measures approximately 432,000 miles, roughly 109 times the radius of Earth. The red giant Sun, with its radius of 1.2 astronomical units, will measure approximately 112 million miles from center to surface. an increase so dramatic that the current Sun could fit within the red giant's radius with room for hundreds of thousands of identical stars. The volume increase accompanying this expansion staggers the imagination. Since volume scales as the cube of radius, a red giant Sun with a radius 200 times larger than the current Sun will have a volume approximately 8 million times greater than its present volume. This means the same amount of stellar material that currently forms the compact, dense Sun will be spread throughout a volume millions of times larger, creating a stellar atmosphere with a density so low that it approaches the vacuum conditions of interplanetary space. Yet despite this enormous expansion in size, the red giant Sun will actually become more luminous than its current incarnation, not less. While the surface temperature drops from approximately 5,800 degrees Kelvin to roughly 3,000 degrees Kelvin, making each square mile of the red giant's surface cooler and redder than the current solar surface. The total surface area increases by such an enormous factor that the overall energy output rises dramatically. Current models suggest the red giant Sun may achieve luminosities 2,000 to 3,000 times greater than its present energy output. This means that despite having a cooler surface temperature, the red giant will flood the inner solar system with energy levels thousands of times more intense than the gentle illumination that currently sustains life on Earth. The inverse square law of radiation ensures that even worlds at greater distances from the Sun will receive energy fluxes far exceeding anything in their previous experience. From the perspective of any surviving outer planets, the red giant Sun will no longer appear as the familiar point source of light that has characterized solar illumination throughout the solar system's history. Instead, the Sun will present itself as an enormous orange disk subtending a significant fraction of the sky, its nearest edge appearing perhaps 50 times larger in angular diameter than the current Sun appears from Earth. The transformation of our star from a compact yellow dwarf to a bloated red giant represents more than just an increase in size. It represents a fundamental change in the character of the solar system itself. The gravitational influence of the Sun remains essentially unchanged, as the star's total mass decreases only slightly through stellar winds during the expansion process. But the energy environment, the radiation conditions, and the physical presence of the central star become utterly transformed. These numbers, precise though they may be, carry profound implications that extend beyond mere astronomical curiosity. When the Sun's surface reaches 1.2 astronomical units from its center, Earth's current orbital distance falls well within the star's extended atmosphere. The question then becomes not whether our planet will experience dramatic changes, but whether it can survive at all in an environment where the boundary between interplanetary space and stellar interior has effectively disappeared. This is the quantitative reality behind the poetic notion of the Sun eating the Earth, not a sudden act of cosmic violence, but the patient expansion of stellar material into regions of space that once held planets, transforming the inner solar system from a collection of discrete worlds orbiting a distant star into the extended atmosphere of a dying giant. The fate of Earth during the Sun's red giant expansion represents one of the most intriguing problems in stellar evolution, a question that cannot be answered through simple geometric considerations, but requires detailed analysis of competing physical processes that operate simultaneously across vastly different timescales. This is not merely a matter of determining whether our planet lies within or beyond the Sun's maximum radius, but rather understanding a complex dynamical system where gravitational effects, stellar mass loss, tidal interactions, and atmospheric drag all contribute to determining Earth's ultimate destiny. The resolution of this question has engaged some of the most sophisticated computer models in astrophysics, producing results that reveal both the precision and the inherent uncertainties that characterize our understanding of stellar evolution. The first complication in predicting Earth's fate arises from the Sun's mass loss during its red giant phase. As the Sun expands and its outer layers become more loosely bound by gravity, stellar winds carry away significant amounts of material into interplanetary space. These winds, driven by radiation pressure and thermal expansion, represent a steady hemorrhaging of stellar mass that continues throughout the red giant phase and accelerates during later stages of stellar evolution. Current models suggest that the Sun may lose 20 to 30% of its total mass during its post-main sequence evolution, with much of this loss occurring during the red giant and asymptotic giant branch phases. This mass loss has profound implications for planetary orbits throughout the solar system. According to Kepler's laws of planetary motion, the orbital radius of a planet is inversely related to the mass of the central star. As the Sun loses mass, the gravitational force that holds Earth in its current orbit weakens proportionally, allowing our planet's orbital radius to increase as the weakened gravitational field can no longer maintain the planet at its current distance from the solar center. The mathematics of this orbital expansion are well understood. If the Sun loses 25% of its mass during its red giant evolution, Earth's orbital radius would increase from its current 1 astronomical unit to approximately 1.33 astronomical units, potentially carrying our planet beyond the reach of the expanding stellar envelope. This outward migration occurs gradually over the millions of years during which the Sun loses mass, providing a potential escape mechanism that could preserve Earth even as the Sun swells to enormous dimensions. However, this straightforward calculation ignores several additional physical processes that complicate the orbital dynamics of planets around evolving stars. If Earth's expanding orbit carries it beyond the Sun's photosphere, but still within the extended stellar atmosphere, our planet would find itself moving through an extremely tenuous but nonetheless real gaseous medium. This atmospheric material, while far less dense than any gas encountered in terrestrial environments, still possesses enough substance to exert drag forces on a planet moving through it at orbital velocities. Atmospheric drag operates through the same physical principles that cause spacecraft in low Earth orbit to gradually lose altitude and eventually re-enter the atmosphere. A planet orbiting within even the extremely rarefied outer atmosphere of a red giant star experiences friction with the surrounding gas, causing its orbital energy to decrease gradually. This energy loss manifests as a slow inward spiral that can ultimately lead to planetary engulfment despite the initial orbital expansion caused by stellar mass loss. Tidal interactions between Earth and the expanded Sun introduce another layer of complexity to the orbital evolution problem. The Sun's enormous size during its red giant phase means that Earth, if it survives the initial expansion, orbits very close to the stellar surface, where tidal forces become much more significant than they are in the current solar system. These forces can transfer energy between Earth's orbital motion and the Sun's rotation, potentially causing additional orbital decay through mechanisms that operate independently of atmospheric drag. The relative importance of orbital expansion, atmospheric drag, and tidal decay depends on precise details of the Sun's mass loss rate, the density profile of its extended atmosphere, and the efficiency of tidal energy transfer mechanisms. These factors vary significantly between different stellar evolution models and remain subject to uncertainties in our understanding of stellar physics during extreme evolutionary phases. The most comprehensive studies of this problem, published in leading astrophysical research journals, have employed sophisticated computer simulations that track all of these competing processes simultaneously. These models incorporate detailed stellar evolution calculations, precise orbital mechanics, and realistic estimates of atmospheric drag and tidal interactions to predict Earth's most likely fate during the Sun's red giant phase. The scholarly consensus that has emerged from these detailed investigations suggests that Earth is unlikely to survive the Sun's red giant expansion. While orbital expansion due to stellar mass loss provides a potential escape mechanism, most models conclude that atmospheric drag and tidal interactions will overcome this effect, causing Earth to spiral inward into the stellar envelope and ultimately be consumed by the expanding Sun. Particularly noteworthy among these studies is the finding that Earth's survival depends critically on achieving a specific orbital radius during the mass loss phase. Models suggest that if Earth's orbit expands to approximately 1.15 astronomical units, our planet might escape engulfment. However, if the orbital expansion falls short of this threshold, or if atmospheric drag proves more efficient than current estimates suggest, Earth will join Mercury and Venus as material incorporated into the dying Sun's outer layers. This represents a remarkable example of how competing physical effects can determine cosmic outcomes through very small margins. The difference between survival and destruction may depend on whether Earth's orbit expands by 15% or only 12%, a distinction that hinges on precise details of stellar mass loss rates and atmospheric properties that remain at the frontier of current astrophysical research. The elegance of this orbital dance between expansion and decay, between gravitational weakening and atmospheric friction, exemplifies how the universe operates through the patient interplay of physical forces rather than through dramatic gestures or sudden catastrophes. Earth's ultimate fate will be determined not by cosmic violence, but by the subtle mathematics of competing effects, each operating according to well-understood physical principles, yet combining to produce an outcome that remains tantalizingly uncertain. The story of Earth's eventual fate under an expanding Sun might seem like an exercise in theoretical physics, a prediction based entirely on computer models and mathematical extrapolation from current stellar behavior. But the universe provides a more direct form of evidence written in the light from distant star systems where similar dramas are already playing out across the galaxy. Through careful observation of other worlds orbiting other stars, astronomers have been able to witness planetary destruction in real time, capturing images and spectra that serve as previews of our own solar system's distant future. These observations transform the theoretical predictions of stellar evolution into documented reality, showing us that the processes we have described are not merely possible, but actively occurring throughout the cosmos. Perhaps the most dramatic example of ongoing planetary destruction can be found in the star system designated KIC 1255758, located approximately 1,500 light-years from Earth in the constellation Cygnus. This system hosts a planet, catalogued as KIC 1255758b, that appears to be actively disintegrating before our telescopic eyes. The planet orbits extremely close to its host star, completing an orbit in just 15.5 hours, placing it at a distance where stellar radiation and tidal forces create conditions hostile to planetary integrity. What makes this system remarkable is not simply the proximity of planet to star, but the observable evidence of planetary material being stripped away in real time. When astronomers monitor the star's brightness as the planet transits across its surface, they detect variations in the depth and duration of the transit that change from orbit to orbit. These variations cannot be explained by a stable, solid planet maintaining consistent dimensions as it passes in front of the star. Instead, the transit variations reveal the presence of a comet-like tail of dusty material streaming away from the planet in the direction opposite to its orbital motion. This tail consists of planetary material, rock and metal, vaporized from the planet's surface by intense stellar heating and then swept away by stellar winds and radiation pressure. The planet is literally evaporating, losing mass continuously as its outer layers are heated to temperatures that exceed the vaporization point of rocky materials. Spectroscopic analysis of this dusty tail reveals the chemical signatures of planetary composition, including silicon, iron, and other elements that characterize terrestrial worlds. The dust production rate appears to vary over time, suggesting that the destruction process operates through complex interactions between stellar activity and planetary surface conditions. Some observations indicate that the planet may be losing mass at rates sufficient to completely erode away within several million years, providing a direct example of how close-in worlds can be entirely consumed by their host stars. Even more dramatic evidence of planetary consumption comes from observations of stellar transients, brief brightening events that occur when stars suddenly increase their luminosity for periods ranging from days to months. One particularly significant event, designated ZTF SLRN 2020, was detected by automated sky surveys that monitor millions of stars for sudden changes in brightness. This transient appeared as an infrared brightening of a star system, accompanied by an optical outburst that lasted several weeks before fading back to normal levels. The characteristics of this event match theoretical predictions for what should occur when a star physically engulfs and consumes a planetary companion. The initial brightening corresponds to the energy release as planetary material falls into the stellar atmosphere and is heated to stellar temperatures. The infrared emission represents thermal radiation from dust created as rocky planetary material vaporizes and then recondenses in the cooler regions of the stellar wind. Follow-up observations of the ZTF SLRN 2020 system revealed additional evidence supporting the planetary engulfment interpretation. The star showed enhanced absorption lines from elements like lithium and calcium that are typically depleted in stellar atmospheres but abundant in planetary materials. This chemical signature provides compelling evidence that the star had recently accreted planetary material, enriching its outer atmosphere with elements characteristic of rocky worlds. The observation of planetary engulfment events like ZTF SLRN 2020 provides direct confirmation that the theoretical processes we have described for the future Sun actually occur in nature. Stars do expand during their evolution, planets do fall victim to stellar consumption, and these events produce observable signatures that can be detected and studied by astronomers. The universe is conducting the experiment that will determine Earth's fate billions of years in the future, and the results are being recorded in the light from distant stars. Perhaps the most poignant evidence of planetary destruction comes from observations of white dwarf stars, the final evolutionary state that awaits the Sun billions of years after its red giant phase. White dwarfs are stellar remnants, dense cores left behind after aging stars shed their outer layers and fade to become slowly cooling embers roughly the size of Earth, but containing most of the original star's mass. Under normal circumstances, white dwarf atmospheres should consist almost entirely of hydrogen and helium, as the intense gravitational field of these dense objects causes heavier elements to sink toward the core within geological timescales. Yet observations reveal that many white dwarfs have atmospheres contaminated with heavier elements, including oxygen, magnesium, silicon, iron, and calcium. These elements can only have arrived recently in astronomical terms, within the last million years or so. The most plausible explanation for this atmospheric pollution involves the disruption and accretion of planetary material by the white dwarf's intense gravitational field. Planets, asteroids, or comets that venture too close to a white dwarf can be torn apart by tidal forces and gradually accreted onto the stellar surface, enriching the atmosphere with the chemical signatures of disrupted worlds. Some white dwarf systems show even more dramatic evidence of planetary destruction. Observations have detected dusty disks surrounding these stellar remnants, formed from the debris of shattered planets ground down to microscopic particles by repeated collisions and gravitational interactions. These disks represent the final archaeological remains of planetary systems that once orbited Sun-like stars, now reduced to cosmic dust, slowly spiraling into their parent star's remnant. These observations across the galaxy provide a sobering perspective on planetary longevity and stellar evolution. The processes that will eventually transform our Sun and potentially destroy Earth are not unique events, but rather common occurrences that play out continuously throughout the universe, documented in the patient light of distant stars. After billions of years of red giant expansion, stellar winds, and the complex gravitational dance that determines planetary survival, the Sun's evolution enters a new phase that represents both an ending and a beginning. Deep within the expanded red giant, where the inert helium core has been steadily growing in mass and density while hydrogen burning continues in a shell around it, conditions gradually approach a threshold that will transform the star's internal energy production once again. This threshold represents one of the most significant transitions in stellar evolution, the moment when helium itself becomes nuclear fuel and the star discovers an entirely new source of energy that can sustain its existence for millions of years beyond the red giant phase. The helium that has accumulated in the Sun's core during its billions of years of hydrogen burning represents the nuclear ash of stellar fusion, the end product of the process that has powered our star throughout Earth's history. Under the conditions that characterized main sequence hydrogen burning, helium nuclei remained inert, too massive and electrically charged to participate in fusion reactions at the relatively modest temperatures of 15 million degrees that sustained hydrogen combustion. Helium fusion requires far more extreme conditions, core temperatures approaching 100 million degrees, and densities that exceed anything the Sun has previously experienced in its evolutionary history. These extreme conditions develop gradually as the helium core continues to contract under its own gravitational weight. With no internal energy source to provide the thermal pressure necessary to halt gravitational compression, the core becomes progressively denser and hotter as stellar evolution proceeds. The hydrogen-burning shell surrounding the core continues to add helium ash to the central region, increasing the core's mass and enhancing its gravitational self-attraction. This creates a positive feedback loop where increased mass leads to stronger gravitational compression, which raises core temperature and density, which in turn creates conditions more favorable for the eventual ignition of helium fusion. The ignition of helium burning, when it finally occurs, represents a fundamentally different type of nuclear process compared to the hydrogen fusion that has previously sustained the Sun. Helium fusion, also known as the triple alpha process, requires the nearly simultaneous collision of 3 helium nuclei to create a single carbon nucleus. This process is far more complex and temperature sensitive than hydrogen fusion, requiring not just high temperatures, but also extremely precise timing and nuclear physics to succeed. The name triple alpha derives from the historical designation of helium nuclei as alpha particles, a term that originated in early nuclear physics research when the true identity of these particles was not yet understood. The process begins when 2 helium nuclei combine to form the unstable isotope beryllium-8, which normally decays almost immediately after its formation. However, at the extreme densities that characterize stellar cores, a third helium nucleus can collide with the beryllium-8 before it decays, creating carbon-12 and releasing energy in the process. This triple alpha reaction exhibits an extraordinary sensitivity to temperature, with reaction rates increasing by factors of thousands or millions for relatively small temperature increases. This temperature sensitivity means that helium burning, once initiated, tends to occur explosively in stellar cores, releasing enormous amounts of energy in a relatively short time period and causing dramatic structural changes throughout the star. When helium burning finally ignites in the sun's core, the sudden energy release will cause the core to expand and heat up rapidly, ending the gravitational contraction that has characterized the red giant phase. This expansion affects the hydrogen-burning shell surrounding the core, changing the temperature and density conditions that sustain shell fusion. The result is a temporary reduction in the star's total energy output and a contraction of its outer layers, causing the Sun to shrink significantly from its maximum red giant dimensions. This phase of stellar evolution, known as the horizontal branch for reasons related to how such stars appear on diagnostic plots used by astronomers, represents a period of relative stability comparable in some ways to the main sequence hydrogen burning that characterized the Sun's earlier evolution. However, helium burning operates on much shorter timescales than hydrogen burning, sustaining stellar energy production for perhaps 100 million years rather than the 10 billion years that characterize hydrogen burning in solar mass stars. The products of helium fusion add new complexity to the star's internal composition. The triple alpha process creates carbon-12 as its primary product, but continued helium fusion can add additional helium nuclei to existing carbon nuclei, creating oxygen-16 through a process known as alpha capture. These heavier elements, carbon and oxygen, become the ash of helium burning, just as helium was the ash of hydrogen burning, accumulating in the stellar core as inert material that will eventually determine the next phase of stellar evolution. The helium burning phase represents the Sun's discovery of a new lease on nuclear life, a temporary reprieve from the gravitational collapse that would otherwise compress the stellar core beyond the point where any known nuclear process could provide sufficient energy to maintain hydrostatic equilibrium. During this phase, the Sun will appear as a somewhat smaller, hotter, and more stable star than during its red giant maximum, though still significantly different from its main sequence appearance. Yet even this new energy source is temporary, limited by the finite supply of helium available for fusion in the stellar core. As helium burning proceeds and carbon-oxygen ash accumulates, the Sun will eventually face the same fuel depletion crisis that ended its main sequence hydrogen burning phase. When the helium in the core becomes exhausted, the star will again be forced to find alternative energy sources or begin the final phases of stellar evolution that lead toward its ultimate fate as a white dwarf remnant. This represents the universe's tendency to provide temporary solutions to seemingly insurmountable problems, allowing stars to continue their existence through successive phases of nuclear burning until no further fuel sources remain available. Each phase operates on shorter timescales than the last, creating a stellar lifetime that resembles a gradually accelerating countdown toward the final cessation of nuclear energy production and the star's transformation into a slowly cooling ember that will persist for billions of years beyond the end of active fusion. As the Sun exhausts its helium fuel and begins the final acts of its stellar drama, the star enters a phase of evolution characterized not by the stable burning that defined its earlier existence, but by a series of increasingly dramatic instabilities that will ultimately tear the star apart from within. These later giant stages represent stellar old age in its most turbulent form, a period when the Sun's internal structure becomes so complex and unstable that the star can no longer maintain the steady energy production that sustained it for billions of years. Instead, the dying Sun begins to pulsate, to vary its energy output on timescales of thousands of years, and most significantly, to shed its outer layers into space through stellar winds of unprecedented intensity. This phase, known to astronomers as the asymptotic giant branch, begins when the Sun faces a fuel crisis more severe than any it has previously encountered. With helium burning exhausted in the core, the star now contains a carbon-oxygen core surrounded by shells of helium and hydrogen that burn intermittently as conditions permit. Unlike the stable burning that characterized earlier phases of stellar evolution, these shell-burning episodes occur in pulses, brief periods of intense energy production, followed by longer quiescent intervals when fusion reactions subside. The pulsing nature of shell burning creates structural instabilities throughout the Sun's interior that manifest as periodic expansions and contractions of the star's outer layers. These pulsations operate on timescales of thousands to tens of thousands of years, causing the Sun's radius, luminosity, and surface temperature to vary cyclically as the star responds to the changing energy output from its interior. During maximum expansion phases, the Sun may swell to dimensions even larger than during its initial red giant evolution, reaching radii that could extend beyond 2 astronomical units from the stellar center. These pulsations drive stellar winds of extraordinary intensity, far exceeding anything the Sun has produced during its earlier evolutionary phases. The mechanism behind these winds involves the complex interaction between pulsation, stellar atmosphere dynamics, and dust formation in the cool outer regions of the expanded stellar envelope. As the Sun's outer layers expand during each pulsation cycle, they cool to temperatures where rocky and metallic materials can condense into tiny solid particles, creating microscopic dust grains in the stellar atmosphere. These dust grains play a crucial role in driving mass loss from the pulsating Sun. Stellar radiation exerts pressure on the dust particles, pushing them outward from the star's surface through the same radiation pressure effects that create comet tails when these icy bodies approach the Sun. As the dust grains accelerate outward, they collide with gas molecules in the stellar atmosphere, dragging the gaseous material along and creating a stellar wind that can remove substantial amounts of mass from the dying star. Current models of this mass loss process suggest that the Sun may shed 20 to 40% of its total mass during the asymptotic giant branch phase, losing material at rates thousands of times higher than during its stable main sequence lifetime. This represents a fundamental transformation in the Sun's character, changing it from a gravitationally bound system that retains its material for billions of years into a star that actively ejects its substance into interplanetary space. The mass loss profoundly affects the Sun's subsequent evolution in ways that distinguish it from the idealized stellar evolution models that assume constant stellar mass. As the Sun loses mass, its internal structure adjusts to the reduced gravitational binding energy, affecting the efficiency of shell burning, the frequency of pulsations, and the maximum size the star can achieve during its most expanded phases. Stars that lose mass more rapidly tend to avoid the most extreme expansions predicted by constant mass models, potentially reaching smaller maximum radii than would otherwise be expected. This has important implications for any planets that might survive the earlier phases of stellar evolution. A Sun that loses substantial mass during its asymptotic giant branch evolution may not expand to the full 2 astronomical units predicted by some models, potentially allowing worlds at Earth's current orbital distance to survive even this final expansion phase. However, the same mass loss that limits stellar expansion also drives the orbital expansion we discussed earlier, carrying surviving planets outward to greater distances where they become less vulnerable to engulfment but also receive dramatically reduced energy from the increasingly distant and variable star. The stellar winds from the asymptotic giant branch Sun create conditions in the inner solar system unlike anything in the star's previous history. These winds carry not just hydrogen and helium, the primary constituents of stellar material, but also heavier elements created through nuclear burning during the Sun's evolutionary history. Carbon produced by helium fusion, oxygen created through further nuclear processing, and trace amounts of even heavier elements synthesized in the extreme conditions of shell-burning episodes all become part of the stellar wind, enriching the interplanetary medium with materials that were once locked in the Sun's interior. The intensity of these winds varies with the Sun's pulsation cycles, creating a complex, time-varying environment where the boundary between interplanetary space and stellar atmosphere becomes increasingly difficult to define. During maximum wind intensity phases, material ejected from the Sun may reach velocities of tens of kilometers per second, fast enough to escape the solar system entirely and contribute to the enrichment of the interstellar medium with elements created during stellar evolution. As this process continues over hundreds of thousands of years, the Sun gradually loses its outer layers, exposing progressively deeper and hotter regions of the stellar interior to direct observation. The star's surface temperature increases as the cooler outer envelope is stripped away, even as the star's total luminosity may decrease due to the reduced mass available for nuclear burning. This creates the conditions for the formation of a planetary nebula, one of the most spectacular phenomena in stellar evolution. The planetary nebula phase represents the Sun's final act as an active star, the moment when the stripped stellar envelope becomes illuminated by the hot, compact core that remains after mass loss removes the outer layers. The intricate shells and filaments of glowing gas that characterize planetary nebulae represent the fossil record of the Sun's asymptotic giant branch mass loss, preserved as expanding shells of enriched material that will disperse into the interstellar medium over tens of thousands of years. This mass loss and the resulting structural changes represent the Sun's gradual transition from a star capable of nuclear burning to a white dwarf remnant that will slowly cool over billions of years. The process occurs not through sudden collapse or explosion, but through the patient shedding of material that leaves behind only the dense core, compressed to Earth-like dimensions, but retaining most of the Sun's original mass. At the end of the Sun's long journey through stellar evolution, after the drama of expansion and mass loss, after the complex pulsations and stellar winds that characterize its final active phases, what remains represents one of the most profound transformations in the cosmic inventory of matter. The white dwarf Sun that emerges from this evolutionary process bears almost no resemblance to the familiar star that once warmed Earth and sustained life throughout the solar system. This stellar remnant, roughly the size of our planet, but containing approximately 60% of the Sun's original mass, represents matter compressed to densities that challenge human comprehension, a final state so alien to ordinary experience that it seems to belong more to the realm of exotic physics than to the celestial mechanics that govern familiar astronomical objects. The white dwarf forms when the Sun finally exhausts its capacity for nuclear burning and sheds its outer layers through the stellar winds we explored in our previous discussion. What remains is essentially the Sun's former core, a sphere of carbon and oxygen nuclei surrounded by electrons, all compressed to a density of approximately 1 million grams per cubic centimeter. To grasp this density, imagine taking the entire mass of an automobile and compressing it into a volume no larger than a sugar cube. This is the typical density of white dwarf material, matter so compressed that a teaspoonful would weigh several tons on Earth. This extraordinary density arises from a form of pressure unknown in everyday experience, something physicists call electron degeneracy pressure. Unlike the thermal pressure that supports normal matter, degeneracy pressure emerges from quantum mechanical principles that govern the behavior of electrons when they are compressed beyond certain critical limits. The electrons in white dwarf material become so tightly packed that they essentially touch each other, creating a resistance to further compression that has nothing to do with temperature, but rather derives from fundamental quantum mechanical laws that prevent particles from occupying the same quantum state. The white dwarf Sun possesses no internal energy source beyond the thermal energy trapped during its formation. Nuclear fusion has permanently ceased, and the stellar remnant can only cool through the slow radiation of heat stored in its incredibly hot interior. The surface temperature of a newly formed white dwarf can exceed 50,000 degrees, far hotter than the Sun's current surface, making it appear brilliant white despite its small size. However, this surface heat represents a finite reservoir of thermal energy that will gradually radiate away over billions of years. The cooling process of white dwarf stars operates on timescales that dwarf even the main sequence lifetimes of their progenitor stars. A white dwarf cools so slowly that even after 10 billion years, roughly the current age of the universe, it will still maintain surface temperatures of several thousand degrees and continue to emit detectable amounts of light. The ultimate fate of white dwarf stars involves cooling to near absolute zero over timescales of hundreds of billions or even trillions of years, far longer than the universe has yet existed. From the perspective of any hypothetical observers in the far future solar system, the transformation of the Sun into a white dwarf represents an almost incomprehensible reversal of cosmic proportions. The star that once dominated the sky, providing warmth and light across astronomical distances, becomes a faint point of light barely visible, even from relatively close distances. The Sun that once subtended half a degree of arc, as seen from Earth, that familiar disk whose daily passage defined the rhythm of terrestrial life, shrinks to a stellar remnant smaller in diameter than our planet. Covering roughly 500 million years, the Sun has brightened by only about 5%. Yet when you expand this timeline to encompass the full geological history of Earth, the cumulative effect becomes profound. The Sun that illuminated our planet when the first bacterial mats began producing oxygen roughly 2.5 billion years ago was approximately 25% dimmer than the Sun you see today. The star that will shine on Earth 1 billion years from now, if our planet still retains its current orbit, will be roughly 10% brighter than the one that currently warms your face. This gradual brightening places Earth in an increasingly precarious position relative to the energy balance that has allowed liquid water to exist on our planet's surface throughout geological history. Earth's climate system has evolved within the context of a specific range of solar energy input, developing complex feedback mechanisms that have maintained relatively stable global temperatures despite dramatic changes in atmospheric composition, continental configuration, and biological activity over billions of years. But this remarkable climate stability depends fundamentally on Earth receiving an amount of solar energy that falls within certain bounds. Too little energy, and the planet would freeze into a permanent ice age, with oceans locked in solid form and life relegated to whatever minimal habitats might exist around geothermal vents. Too much energy, and the delicate balance that allows water to remain liquid at Earth's surface would be overwhelmed, leading to runaway greenhouse conditions that would eventually boil away the oceans entirely. Earth currently occupies what astronomers call the habitable zone around the Sun, the range of orbital distances where liquid water can theoretically exist on a planetary surface. But this zone is not fixed in space. As the Sun gradually brightens, the habitable zone slowly migrates outward, moving away from the Sun as increased stellar luminosity makes inner regions too hot to support liquid water. This migration occurs so slowly that it would be invisible to human observation across thousands of generations. Yet it represents a fundamental shift in the solar system's architecture, a quiet rearrangement of the conditions that determine where life can exist. Earth, locked in its current orbit by the gravitational dynamics of the solar system, cannot migrate outward along with the habitable zone. Instead, our planet will gradually find itself receiving more solar energy than its climate system can accommodate through natural regulatory mechanisms. The universe, it seems, rarely ends things with explosions or dramatic catastrophes. Instead, it tends to conclude chapters through increments, through the patient accumulation of small changes that eventually cross critical thresholds. The death of Earth's habitability will not announce itself with spectacular fireworks or sudden transformation. Post-main sequence evolution lasts perhaps 1 billion years. Its white dwarf cooling phase will continue for hundreds of billions of years, slowly fading from white to yellow to red and eventually to a cold, dark object invisible except through its gravitational influence. As we reach the end of our journey through the deep future of the Sun and the ultimate fate of Earth, we arrive not at a destination, but at a vantage point from which the entire story takes on a different character. The timescales we have explored, measured in billions of years, represent durations so vast that they challenge the fundamental ways humans typically think about permanence, change, and the meaning of existence itself. These are not merely large numbers, but glimpses into a cosmic perspective that reveals both the temporary nature of everything we consider permanent and the extraordinary rarity of the conditions that have allowed life to flourish in our small corner of the universe. The first revelation that emerges from this cosmic perspective concerns the true nature of Earth's habitability. Throughout human history, and indeed throughout the entire evolutionary history of life on our planet, the conditions that sustain liquid water and complex chemistry have seemed like fundamental features of the world, as basic and reliable as gravity or the rotation of Earth itself. Yet our exploration of stellar evolution reveals that habitability represents not a permanent characteristic of our planet, but rather a temporary chapter in Earth's biography, bounded by the gradual brightening of our Sun and the slow evolution of stellar physics over geological time. This habitability window, spanning perhaps 8 to 10 billion years from Earth's formation to the moment when rising solar luminosity renders the planet uninhabitable, represents an extraordinary gift of cosmic timing rather than an inherent property of rocky worlds orbiting sun-like stars. The Earth that nurtured the first bacterial mats 3.5 billion years ago, the Earth that will witness the last complex organisms perhaps 1 billion years from now, and the sterile Earth that will orbit within the red giant sun's atmosphere. Billions of years after that are the same world, following the same orbital mechanics, receiving energy from the same star. Only the intensity of that energy changes slowly and inexorably, according to the mathematics of stellar evolution. The second revelation emerges from our examination of planetary destruction around other stars throughout the galaxy. The stellar evolution processes that will eventually transform our Sun are not theoretical predictions based solely on computer models and mathematical extrapolation, but rather observable phenomena documented in the light from thousands of distant star systems. The evaporating planets, the stellar engulfment events, the white dwarf systems surrounded by the debris of former worlds all serve as external confirmation that the future we have described for Earth represents not speculation, but documented reality occurring continuously throughout the universe. This observational evidence transforms the abstract predictions of stellar physics into a tangible cosmic narrative, showing us that Earth's story, while unique in its specific details, follows patterns that characterize planetary evolution around sun-like stars across the galaxy. We are not witnessing the unfolding of some unprecedented cosmic catastrophe, but rather participating in one iteration of a story that the universe has been telling for billions of years, written in the physics of stellar cores and planetary atmospheres, enacted around countless stars throughout the Milky Way and beyond. The third and perhaps most profound revelation concerns what this cosmic perspective means for our understanding of life, consciousness, and human existence within the larger context of cosmic evolution. The enormous timescales of stellar evolution, spanning tens of billions of years from main sequence birth to white dwarf cooling, provide a temporal framework within which the entire history of life on Earth occupies only a tiny fraction of cosmic time. Yet this brief interval, This momentary flowering of complexity and consciousness in a universe dominated by the slow burn of nuclear fusion and the patient cooling of stellar remnants represents something extraordinary precisely because of its rarity and temporal brevity. The universe operates primarily through processes that occur over billions of years. The slow accumulation of helium ash in stellar cores, the gradual brightening of main sequence stars, the patient expansion of red giants, the leisurely cooling of white dwarfs. Against this backdrop of cosmic time, the rapid evolution of life, the emergence of intelligence, and the development of consciousness represent phenomena that occur on timescales so brief that they might seem almost instantaneous from the perspective of stellar physics. Yet it is precisely this brevity that makes life and consciousness so remarkable within the cosmic context. The universe spends billions of years creating the chemical elements necessary for complex chemistry. Billions more years forming planetary systems where those elements can combine into intricate molecules, and additional billions of years maintaining stable energy environments where complex systems can evolve and persist. All of this vast expenditure of cosmic time and energy culminates in brief moments, cosmically speaking, when matter organizes itself into forms capable of contemplating their own existence and understanding their place within the larger story. This perspective does not diminish the significance of human life or consciousness, but rather places these phenomena within a framework that reveals their extraordinary nature. Every moment of awareness, every instance of understanding, every act of love or creativity or scientific discovery occurs against the backdrop of a universe that spent billions of years preparing the conditions necessary for such experiences to exist. The fact that these experiences are temporary, that the conditions supporting them will eventually change as stellar evolution proceeds, does not reduce their meaning but rather emphasizes their preciousness. The red giant sun that will eventually remake the inner solar system, the white dwarf that will slowly cool over hundreds of billions of years, and the cold dark remnant that will persist long after the universe itself has changed beyond recognition, all represent chapters in a cosmic story that began with the first generation of stars and will continue until the last stellar remnant fades to invisibility. Within this vast narrative, Earth's brief tenure as a living world represents a moment of extraordinary complexity and beauty, a temporary organization of matter and energy into forms capable of understanding and appreciating the very cosmic processes that created them. This is the perspective measured in billions of years, not a reduction of human significance, but rather a recognition of the remarkable cosmic circumstances that have allowed consciousness to emerge and flourish, however briefly, in a universe otherwise dominated by the slow, patient processes of stellar evolution and cosmic expansion.